Welcome to the Antonio Zamora podcast that discusses a variety of scientific topics. The Younger Dryas Comet. How big was it? This video discusses the Younger Dryas impact that killed the North American megafauna and evaluates methods for calculating the energy of the impact to derive the size of the asteroid or comet that caused the cataclysm. A 2007 paper by Richard Firestone and 25 co-authors introduced the Younger Dryas impact hypothesis and proposed that an extraterrestrial impact over North America 12,900 years ago contributed to the megafaunal extinctions and the Younger Dryas cooling. The paper stated that the evidence pointed to an extraterrestrial event with continent-wide effects, especially biomass burning, but that the size, density, and composition of the impactor were poorly understood. Firestone's paper relied on a 1997 publication by Toon et al., which calculated that an impact capable of continent-wide damage requires energy of 10 to the 7th megatons or 10 million megatons. This is equivalent to an impact by a comet with a diameter greater than 4 kilometers. The calculation of a convergence point of the Carolina Bays and the Nebraska rainwater basins at Saginaw Bay made possible the development of the glacier ice impact hypothesis, which provided a new estimate for the energy of the extraterrestrial impact. The glacier ice impact hypothesis, published in the journal Geomorphology in 2017, describes four mechanisms by which the Carolina Bays may have formed. First, a meteorite impact on the Laurentide ice sheet ejected ice boulders in ballistic trajectories. The secondary impacts by the ice boulders liquefied on consolidated ground close to the water table. Oblique impacts of ice boulders on liquefied ground created inclined conical cavities, and viscous relaxation reduced the depth of the conical cavities to produce shallow elliptical bays. Pictures of the experimental impacts contributed to the acceptance of the hypothesis for publication in the peer-reviewed journal. A detailed study of the Carolina Bays by William Prouty in 1952 estimated that there were 500,000 bays in the Atlantic coastal plain and that the bays covered 50% of the surface. This estimate was done from aerial photographs. The number of bays estimated by Prouty was used to calculate the energy of the extraterrestrial impact and the size of the impactor. The ballistic trajectory associated with each Carolina Bay is used to calculate the speed of the ice projectile, which is then used with equations relating energy to crater size to calculate the energy that formed each bay. The law of conservation of energy allows us to combine the energy of all the bays to estimate the energy of the extraterrestrial collision. The combined energy associated with 500,000 Carolina Bays is approximately 6.35 times 10 to the 21st joules, or 1.5 times 10 to the 6th megatons of TNT. This is one order of magnitude less than the 10th to the 7th estimate given in the Firestone paper. The kinetic energy of 1.5 million megatons corresponds to a stony asteroid with a diameter of 3 kilometers or to a faster comet with a diameter of 2 kilometers. The combined volumes of the glacier ice projectiles also provide an estimate of the volume of the ice ejected and the size of the circular area containing this volume of ice. These calculations underestimate the energy of the extraterrestrial impact because now we know that there are more than 500,000 Carolina Bays. LiDAR, which is a laser-based imaging technology, has revealed that the Carolina Bays cover 100% instead of just 50% of the surface of the Atlantic coastal plain. Prouty's estimate of 500,000 Carolina Bays grossly underestimated their number, but he did very well considering that he only had aerial images. LiDAR has given us a much clearer view of the surface of the Earth. Before describing the new method of estimating the energy of the Younger Dryas comet, it is useful to review the mechanism of impact cratering. The first stage begins when the projectile contacts the target surface. The swiftly moving projectile pushes target material out of its path, compressing it and accelerating it to a large fraction of the impact velocity. At the same time, the target's resistance to penetration decelerates the projectile. The shock pressures reach hundreds of gigapascals and exceed the yield strength of both the projectile and the target. The projectile and the target melt or vaporize during the great explosion that results from the release of such pressures. The excavation stage begins immediately after the contact and compression stage. A hemispherical shock wave propagates through the target, creating a circular crater. Material is ejected in the form of an expanding conical ejecta curtain. The innermost ejecta are launched first, and travel fastest in parabolic trajectories. Ejecta originating further from the center are launched later and move more slowly, falling nearer the rim. This image illustrates how large, heavier material falls closer to the impact point and small, lighter material falls further away. Later, we will see that the Carolina bays differ from this size distribution, which influences the calculation of the energy of sedimentation. The program to calculate projectile size from crater diameter assumes that the crater is circular. By equating the area of a circle to the area of an ellipse, we find that the equivalent radius of the ellipse is the square root of the product of its semi-major and semi-minor axis. The diameter of the ellipse can then be used to calculate the projectile size. Professor J. Meloche and Ross Bayer developed a program to calculate projectile size from crater diameter based on yield equations relating energy to crater size. The program requires the crater diameter, the impact velocity, the angle of impact, and information about the physical characteristics of the projectile and the target material. The energy of the ballistic sedimentation can be calculated if we select an area with bays, calculate the energy to create each bay, get the total energy for the area, calculate the energy per square kilometer, and multiply times the whole area of sedimentation. However, we have to take into consideration that the ice bombardment was not distributed evenly. The problem of uneven distribution of impacts can be addressed by dividing the landscape into circular bands. This image shows 3 circles with a center at Saginaw Bay and radii of 500, 1000, and 1500 kilometers. We can now calculate the energy of the secondary impacts per unit area in each band and multiply times the area of the band. The first circular band between the 500 and 1000 kilometer mark includes New Jersey. The Laurentide ice sheet covered Canada at the time of the extraterrestrial impact, so the secondary impacts on the ice sheet left no trace. Nevertheless, the calculation assumes that the complete band received a typical number of impacts. This band has an area of 2,356,194 square kilometers. The Carolina bays in New Jersey are relatively small. They typically measure from 100 to 200 meters. These bays are a little bit bigger than a football field. The second circular band between the 1,000 and 1,500 kilometer mark includes the Nebraska rainwater basins and the Carolina bays in North and South Carolina. This band includes the largest bays and has an area of 3,926,990 square kilometers. In Nebraska, the bays are difficult to count because most of the bays smaller than 4 kilometers have disappeared due to erosion, but we can compensate by using the density of the bays in the portion of the band along the east coast. Only large bays have been preserved in Nebraska. Rainwater flows over the rough terrain and erodes the bays. In the Atlantic coastal plain, where the bays have been well preserved, the terrain is porous and fairly level, so the water cannot flow fast horizontally along the surface. Rain percolates through the soil and flows to lower terrain via underground aquifers. Originally, I was going to calculate the energy for a square with size of 10 kilometers, but the number of bays was so large that I constrained it to 5 kilometers, which is 1/4 of the work. I used the Carolina Bay survey provided by Michael Davies, which marks the center of the bays with tiny circles. Clicking on these tiny circles displays the length of the major axis of the bay and other information. I was able to use this length and avoided having to measure each bay individually with Google Earth. The next task was to number all the bays whose center was within the 25 square kilometer area. At this level of magnification, some small bays are not counted. However, by counting the major impacts, we will have a rough idea of the energy transferred by the ballistic sedimentation to the area. This image shows the results obtained by applying ballistic equations and the projectile size calculator for bays number 32 and 35. The small bay, number 32, with a length of 602 meters, was created by an impact of 1.2 megatons. The larger bay, number 35, with a length of 1,613 meters, was created by an impact of 44.3 megatons. By comparison, the most powerful hydrogen bomb ever tested was the Soviet Union's Tsar Bomba, with a yield of 50 megatons. It seems logical to conclude that the saturation bombardment by the glacier ice that created the bays killed the megafauna from the east coast to Nebraska. It is always necessary to verify the results of a numerical model. How do we know that the numbers that we obtained from the calculator are right? The best way to check if the projectile size calculator produces reasonable results is to compare against experimental results. I drew ellipses at a 1 to 1000 scale on a sheet of paper, and I added circles for the calculated projectile size. The comparison with the experimental results on the right shows that the calculated projectile sizes have a similar ratio relative to the base size. Therefore, the results based on this calculator are likely to produce adequate estimates. Calculating the impact energy for each Carolina bay is labor-intensive. Some of the large bays had impact energies much greater than the Tsar Bomba. After adding up the energy for all the bays within the 25 square kilometer area and dividing by 25, we conclude that the impact energy per square kilometer is 21.4 megatons. Multiplying this number by the area of the Carolina band, we get a total impact energy of 1.1 times 10 to the 24th joules, or 8.4 times 10 to the 7th megatons. This number is in the range mentioned in Firestone's 2007 paper as capable of inflicting continent-wide damage. The procedure for calculating the energy of emplacement for the Carolina bays in New Jersey is the same. In this case, only 1 square kilometer was selected and the bays were assigned numbers. The impact energy in the 1 square kilometer area of New Jersey does not add up to 1 megaton. The impact energy is only 393.6 kilotons per square kilometer, but that is enough to kill all the megafauna and Clovis people in the area and grind them up into a pulp. The total impact energy in the New Jersey band is 927,327 megatons. While this is a large number, it is only 1/100th of the energy in the Carolina band. We only need to use the energy of the Carolina band to calculate the size of the Younger Dryas impactor. We now have all the information necessary to calculate the size of the Younger Dryas impactor. The formula for kinetic energy, K equals 1/2 mv squared, is used to calculate the mass of the projectile. A comet with great speed has a smaller mass compared to a slower asteroid with the same kinetic energy. The mass divided by the density provides the volume. Using the formula for the volume of a sphere, we can determine the radius of the impactor, and multiplying by 2, we get the diameter. Notice that for these calculations we have assumed that the impactor had a density of rock. The final result is astounding. According to these calculations, the extraterrestrial impactor that created the Carolina bays was an asteroid with a diameter of 17 kilometers traveling at 17,000 meters per second, or a comet with a diameter of 8.3 kilometers traveling at 50,000 meters per second. The asteroid would be about the size of Washington, D.C. Comets are icy bodies which are less dense than rocky asteroids. Using the density of ice of approximately 1,000 kilograms per cubic meter, we calculate a bigger volume and a diameter of 12 kilometers for the comet. This image shows a 17-kilometer wide asteroid and a comet with a diameter of 12 kilometers compared to the District of Columbia. It is amazing that such relatively small extraterrestrial objects can have such a profound effect on life when they collide with the Earth. The study of the Carolina bays is a work in progress. Each time that we examine the bays in greater detail, we always discover something, and we get new insights about the terrible day 12,900 years ago when the Earth and a comet crossed paths and changed the course of human history. The different sizes and morphologies of the Carolina bays record the story of the Younger Dryas cataclysm. It will take diligent study to interpret the geological features and find out what really happened. Much time has been wasted arguing that the Carolina bays were created by wind and water mechanisms over thousands of years. Well-preserved Carolina bays and Nebraska rainwater basins have elliptical geomorphology, and this implies that they originated as inclined conical cavities. It is time to move forward and thoroughly investigate the impact origin of the Carolina bays. Thank you for listening to this podcast. Please visit the YouTube channel or the website for many other interesting topics.